Welcome to the Bayesian reliability class. In today's talk, I will present techniques for analyzing reliability data using Bayesian perspective. I will focus on assessing reliability of components with particular attention to models. So we must begin with defining probability. There are various and different in-depth definitions of reliability. However, a common feature of definition for reliability must account for whether or not an item performs at or above a specified standard. That standard in terms of time is called a mission time, or in terms of industry, this mission time is usually known as warranty period. So considering the mission time, one measure of reliability could be a reliability function. Reliability function at time t can be defined as probability that the lifetime of the component survives beyond time t. So we'll say it has survived at least till time t. Notationally, if small f here represents the probability density function, then this reliability function can be defined as such. We realize that the definition in terms of probability, therefore reliability function, must always fulfill the restriction that it lies between 0 and 1. Thus, corresponding CDF, if we look at definition of CDF, it can be termed as unreliability function. We can begin with a simple example. Assuming that the component in which we are interested to determine its failure time follows an exponential density function. For a lifetime t, which has to be essentially non-negative. And now for this component for which we are already aware about the model, which is followed by this component's lifetime, we are interested in finding whether this survives its warranty period, which means it lives at least up to its warranty period, which is 6 months. In terms of hours, it can be converted into 4380 hours. And we are interested in finding that it fails before the end of the first year. So 1 year in terms of hours works out to be 8760 hours. So this particular statement about the component, we are interested in finding the survival of the component after warranty period, which is 6 months, but before end of the first year. Now, to evaluate this, the time points, the density function, and we integrate with respect to the span of the lifetime in which we are interested. After a little mathematics, the integral works out to be, this indicates that probability of failure of this particular component which follows this exponential distribution during the interval from 6 months up to 1 year is 23.7%. So this is the kind of assessments we are able to make in the reliability measurement. Now, I would like to show that it is up to the modeler to assume the model. Now, how we do it, we will cover it in later course, but we want to focus here on the concept that if time to failure is described by an exponential failure time density function as described above, then this time, instead of a fixed value, we take the parameter to be theta, assuming that theta is positive, continuous. This will lead to a reliability function using this definition, FSDS from t to infinity. This will lead to a reliability function using the above definition after doing some integral steps. So for an exponential distribution of this form, we will always have a fixed expression for the reliability function. Now, if the same component's lifetime is described by, say, some other distribution, say Weibull distribution, another popular lifetime distribution in reliability data, then we know the model to be of the form it is a kind of a generalized exponential distribution where we have one more shape parameter. With the same restriction. In this case, the reliability function works out to be, using the earlier definition, the same definition as, in place of now the PDF of exponential, we will be replacing PDF of Weibull. So again, we working out the arithmetic, we find that this will have a totally different form. Right? So, given a particular failure time density function, reliability function can be obtained directly. This illustration helps us to know this small fact. Right? Now, we understand that reliability function is one way of assessing reliability formally. The other way, which is again a very popular metric among the practitioners, is the hazard function. Hazard function is also known as instantaneous failure rate hazard function, denoted by small h, which is ratio of PDF and the mission time, or the reliability function. This hazard can have different shapes. Its types are, it can be increasing hazard, it could be a decreasing hazard, or it could be a bathtub shape hazard. It can even be a constant hazard. So what we mean to say is, if the time increases, then the failure risk keeps on, the failure rate keeps on increasing. This is IFR, increasing hazard rate. Opposite is the case in the decreasing hazard rate. We see that the hazard is falling as the time is progressing. It is also possible that we have a constant hazard rate. That means as the product ages, its efficiency, its future survival, its future reliability does not undergo change. So this particular context is illustrated through the terminology known as constant hazard. The gradient does not change. Then comes the bathtub failure, where we see all the three are incorporated. Initially, we see this is kind of an hazard, and here we see this is again kind of a hazard, where in the smaller time there is a higher hazard. Here again in the small n time there is a higher hazard. However, in the middle, we see the hazard is almost constant. There is no change. Okay, so this is kind of the lifetime period where things go smoothly. The component functions smoothly. Normally, the industry is interested in a third kind of representation known as average hazard rate. Average hazard rate, as the name implies, always calculated between two time points. So, it is nothing but difference of the individual hazard rates at the 2 time points divided by the time elapsed between the 2 time points. So, logically, what we understand is hazard rate is instantaneous at one point, failure rate, whereas average hazard rate covers a period and indicates the average hazard experienced in that period by the particular component. Mean time to failure. This is another very popular metric in the industry to relate to the reliability of a particular component. Mean time to failure is defined as expected T, mean time, expectation. By definition, time going from 0 to any future limit, for convenience let us write infinity, because we know that given a particular component at some time point in future which is very large, the operating time, after a finite amount of operating time, we will have the component as either gone out of function or gone out of time developments according to the technological standards. So, this infinity is accommodated to incorporate those ideas. However, it will remain finite, we understand, through the logic. So, this is a kind of a definition, MTTF. Right? So, we will come back to this. If we let Ft, because we had related Rt earlier to be equivalent to 1 minus Ft, right? So, if we can represent Ft as this, then MTTF can be recast as negative of or Now this first term, this is 0 at both the limits. It is 0 here, it's fine. But it is 0 because at the upper limit also, since the system, as I said just now, must fail after a finite amount of operating time. Therefore, we must always have TRT converging to 0 as t becomes very large. So what is remaining is only the second term. So MTTF can be characterized as this, or directly, if we are able to find a closed form of FT for that particular model which we are considering, then MTTF can also be directly computed as this. Now in general, see, here I have defined MTTF as the expected lifetime, right? In general, if lambda t, for example, a function of t, lambda, a function of t, which means it is not fixed, it changes with time. So in general, if lambda t is defined as the failure rate function, then by definition, we must not directly infer that MTTF is reciprocal of this, reciprocal of the failure rate function. We must not interpret this. So this is a caution. This is a point to be noted. MTTF should be used when the failure time distribution function, which is specified because the reliability level which is implied by the MTTF will always depend on the failure time distribution that we are using, as we found above for the case of Weibull as well as the case of exponential distribution here, right? So MTTF is strongly linked with the RT, the reliability measure of the underlying failure time distribution. RT is going to change forms as the model is changed. So, although MTTF measure is one of the most widely used reliability calculations, we have to use it with caution, and we cannot use it always to imply this is the guaranteed minimum lifetime. It will always depend on the context. So, as a remark, as an example for this remark, we take an example where a 12 components from some mechanical parts are taken. 12 mechanical components are taken. Now, we have measured individual lifetime of all these mechanical components. So, these are the individual lifetimes and these have been recorded. So, when we add all these, we get the total lifetime of the 12 components. To get average lifetime of the 12 components, right? Average lifetime of the 12 components, what we do is, we simply do the arithmetic mean, right? So, let us say it comes out to be, say, 3660 hours if the summation or the total lifetime is, say, 43920 hours. But it may happen that out of these 12 components, any one may have failed at a very early time, which is far away from the average. Others may be in this realm, in the neighborhood, but one may have failed very early. So this is why I have cautioned that MTTF cannot be interpreted as the guaranteed minimum lifetime, and it can also not always be computed as the inverse of the mean failure time. Fine. So these are the two cautions that we exercised before we move ahead. The next metric can be not so popularly used, but it could be a measure It's called quantile. So when it is used, quantile we understand by definition, quantile Q, or equivalently we can say, so it is the time, quantile is that time by which a specified proportion of the population fails. Okay, I repeat, quantile is that time Q by which time a specified proportion of the population fails. If CDF is flat over some interval, then we define Q as the earliest time for which FQ will be equal to P. Right? If CDF we know is an increasing function, but somehow in some portion it becomes flat. Then the portion where it starts to become constant, for this the value quantile will be taken as the earliest time when it started to go flat. So reliable life is the time for which 100 R% of a population will survive, where R is a specified proportion between 0 and 1.